Hi everyone, thanks for joining today. This is Spencer with Adapt Software. Everyone should be able to see my screen. I've shared that, and today we're going to continue with part 2 of the one-way slab and beam example that we had set up last week. Just a few announcements. This is related strictly to gravity only design, so we're going to talk today about generating the strips in the one-way slab direction, and then also add post-tensioning to the beams and also the slabs, and then we'll go ahead and process the design of the slab and beams and look at some results for this example. The video will be placed up on youtube.com, Adapt Support's YouTube page or channel, and it will be placed in the webinars folder. For questions, feel free to ask questions. If you can, please reserve them to the Q&A session at the end of the meeting, and I'd be happy to answer questions then. And then also, if you have questions that are different or let's say not applicable to the meeting today, if you guys don't mind, please just reserve those to submitting those to our support staff at support@adaptsoft.com. So we're going to go ahead and get started. I'm recording the meeting now. And last week we ended up by adding support lines that we essentially imported the model from Revit. We're looking at a single level of that model, and we kind of idealize this model as flat slabs, where in reality there are ramps that will connect the slabs for this particular parking. But for the gravity only design, we're going to look at this in single level mode and isolation for level 3. And we had loaded the structure. We had modeled some openings here that kind of disconnect the slabs, where you have the ramping out on the outsides and then the flat portion in the interior. We generated design strips for the Y direction. So if I go into a plan view and we go to floor design, I can turn on these strips, and these strips are all beam design. So if we select one of the strips, we can see that this is a T-beam with some flange. If we go to the design tab, this is going to be designed as a beam, meaning the program will apply code requirements relative to beam design for the gravity design of the member. We're going to jot down one thing here while we're inside of this dialog. This is the support line dialog. If we go over to design sections, I want to just take note of the area of one of these beams, and we're going to use this to determine the initial amount of post-tensioning we're going to add to the beam. So if we go to details here, we can see the area is 3,040 square inches, and we'll note that before we get into modeling the PT, we have to lay out the support lines in the X direction. So I'm going to just turn off the support lines in both directions, and we'll go back to the strip modeling, and I'll create a support line in the X direction, which I'm going to replicate and copy down. And this support line will be labeled as a one-way slab. So if we go to the design, we're going to set this to one-way slab criteria, and I'll go ahead and just model the first support line right on the perimeter of the slab. And I'm going to choose arbitrarily just a spacing, kind of a unit strip spacing for my support lines in this direction. My bays for this slab, let me pull out this marking tool here, dock that over there. So this is 30, and then we have 60, and then those are dimensioned down here. This is symmetric about this axis. So we'll go ahead, and I'm going to actually break this into 10-foot strips. So I'll take this support line, and I'll use the modify copy option to copy that down. We'll use a -10, that's in the negative Y direction, and we're going to copy this 15 times. We'll say copy. Okay, I need to copy it just a couple more times here. we'll copy that again. And now we have support lines for the one-way slab direction. And those support lines are snapped on the edge of the slab to each interior beam, which is what we're considering a support for the one-way slab. Okay, and once that's input, now we can generate our design strips for all for both directions. Now here we have an issue where it says two support lines are without design sections, essentially, where there's only two design sections on these two support lines. So we have some issue here with the X direction strips. I'll just isolate one of the directions here. And let me go back and delete these out. And what I probably forgot to do is change the direction of these strips. So if we go to general, you can see we still have this set to Y direction. So how do we remedy that? I'll first just isolate my support lines only. So I'll turn off slab, walls, columns, and openings, and beams. There's beams also. And I'm just going to window select these. Those are the X direction support lines that I inadvertently set to Y. So I'll change this. I'll go back to modify selection. And we're going to select support line, and I'll just change these to X. So those have to be designated the proper direction. And then I can go back to my default display, and under floor design again, I'll generate the sections one more time. So now we have sections that look proper for this one-way strip direction. It's really up to the user. I would not, for a one-way slab, I would not only put support lines on the column lines, because you're integrating over too wide of a strip, including a portion out in what I would say kind of a mid panel and then over at a support location. So you want to break this up into more strips. 1 foot spacing is probably too much. 5 to 10 foot spacing in this case would probably be a good value for the strip spacing for a one-way slab. Okay, so now we have our strips. We're going to add post-tensioning. So we'll start with the beam direction. I'll go back and just turn off my strips, and we're going to add PT to these beams. Now we're going to make just some assumption. We're going to go to the tendon tab. We're going to add PT, but we need to know what we can add. We need to know how many post-tensioning strands, or what the total force will be, the effective force for these cables. And to do that, we can either map banded tendons to strips, or we can just, as a user, we can make some, educated assumption as to what starting point we want the tendons to be at. And that's what we'll do. We'll assume that for an interior beam, we have an area of 30,040 square inches. So if I multiply that by a target minimum precompression, and for our beams, I'll say that's 150, I get a required force of 456 kips. That's a average effective force, or total effective force, for my beams on the interior. And I realize that, for example, this beam doesn't have quite the same tributary as these beams here, but we're gonna just apply this to all beams except for the perimeter, and we'll actually just cut that force in half. So we have 456. And we have to make a decision as to what the effective force is going to be. So we're going to say we're going to use 1/2 inch diameter cables. 270 KSI is FPU. That's the ultimate strength of the cable. If we assume a jacking ratio or a jacking value of 0.8 FPU, then we get down to about 216 KSI. And our assumption is, beyond that, we're going to have another 40 kips per square inch of loss in the cable. That gets us to an effective average force, or stress rather, of 175 KSI. And if we multiply that by the area, we get about 26.7 kips. So we'll use that. In reality, if these are single pull tendons, your loss might look something like this. then you get, you know, some seating loss over some distance x. And if we say, well, this is the maximum force here at 0.1, this is the minimum force 0.2, we could also say, well, there's also some average force. And this average force, this blue line, is what we're assuming the force is going to be in that cable after all losses have occurred. That's both short-term loss and long-term loss in the cable. So we'll say if we take 456 kips, which is our requirement to meet minimum P over A, we divide that by 26.7. We need 18 strands in each interior beam. So I'm going to model 18 strands. I'll go ahead and set up my pre-stressing criteria first. I have 270 FPU, 240 KSI for my yield stress of the cable. My modulus, I'm going to modify to 28,500. I think that's more in line with typical standard value for modulus for the PT steel. My allowable stresses for the post-tensioning for beam is set here, 7.5 times square root of F prime C for sustained and total, and this is tensile allowable versus compression allowable. We also have an allowable stress at initial condition when the force is transferred, so the program will check against those stresses. We go to tendon heights. We're going to assume for the beam, we'll say that the tendon heights will be 1.5 inches. This is to the CG of the tendon group. So if I have 18 strands, then the CG to that set of strands, whether they're laid out, you know, as flat bundles, you might have 1 bundle, 2 bundle, 3 bundle. This is the bottom of the beam. Let's say this CG to those 3 flat bundles might be 1.5 inches. So make sure that you know you recognize how those might be detailed and laid out and have the proper setting for the CG. And we'll use 1.5 here. So once that's set up, I'm going to add a tendon and then I'll replicate it. For this first line, this is going to be a continuous tendon through. I'll start at the bottom and I'm just going to snap on my column locations. These are basically the high points, and then the 2 end points are the CG. Those are the anchors for the tendon. These tendons here are a little bit different, so I'll just skip over to this one. This becomes the same thing. I'm not really worrying about the number of strands yet. I'll make that modification in a moment. These tendons need to be discontinuous. So I'm actually going to model from here to there. Actually, let me backspace to there. And then I'll model from this point over to here. This is a 2-span tendon. And then I'll start again and model this one to here. Okay, these are essentially single span beams because there's a break in the slab due to the ramping. So we're modeling the tendons this way. Now if I select these tendons that I had just input, I'm going to copy them. So I'll just Control C, Control V. The program will allow us to select a reference point, which will be there, there, and there. Okay, if I go to a view, a 3D view, you can see the profile of the cables in this view. And now I want to set the number of strands for each of those modeled tendons. So we'll go in and I'm going to use the tendon editor to do this. I'll open the editor. I'll go over to force, which can be input as number of strands or total effective force per cable. Here, the cable needs to be set to 18, right? So we're going to say, well, we want to set the number of strands first. So I'll set this to 18. And then if I just window select the endpoint, that will change the number of strands to 18 for those 6 or 7 cables we added. Okay, and then once the number of strands is set, if I wanted to adjust the effective force, I could always adjust that here, and then window select again, or just spot select the cables. Now, notice that if I go back to number of strands, you have to be careful. These are, again, discontinuous. So I need to make sure I also select these cables, and I'll select those cables, and that should change those to 18. So this tag will be shown at the start point of each tendon, and these look continuous, but they're really not. So that's a little bit of a trap, if you will. The text is a little small. I'm going to change the text under visibility, view settings. The tendon option is under the finite element tab, and we'll go over here to symbol size. I'll increase that by half, and then I'll change the font size to 12. And now when we go back into the editor, you should see this text is a little bit larger than it was previous. So if we wanted to change the CG, we could do the same here. Once we switch over to CG, these are all currently set to 1.5 for our CG, and we're going to leave those as they are currently. The other thing I want to note, and I'll pull up this cable right here as our example. Because this tendon starts and stops at a beam, the beam is 36 inches deep. The program just anchors that at the CG of the element that it's referencing. So in this case, it references it at the beam, therefore it takes 36 over half of 36 is 18. And in reality, that beam is really a T-beam. There's a flange there, there's slab. So if I wanted to adjust the CG at the anchors, I would have to determine where that is located. And the best way to do that in the software is to go back to the design strips. So in this particular span right here, or this beam, if I go to design sections and details again, and I could have jotted this down previous, I just was not thinking that far ahead. The CG, the centroid to the top fiber is 7 inches. That's shown right there. And then on the interior beams, where we have a little bit wider of a tributary, the CG is 6.59. I'm just going to round it to 6.5. Okay, so we're going to change the CG for these cables on those ends. I'll go back and just turn that off. And let me change the text again. It was a little bit too. Let me just bump that up to 30. I'll go back to Tendon Editor, CG. Okay, these are set currently to 18. I'm going to first change this to 7. This is from the top of the beam. This is not from the bottom. Whenever you change a CG in this view, it's always referenced similarly to the window for an individual tendon. One thing to note is if I let me just close that just for a moment. If I view the tendons from the display manager, look at the control points, these are always referenced from the bottom up. Okay, so if you're wanting to print out, let's say, the tendon layout with the CGs, you would want to use display manager if you're always referencing the control points from the soffit upward. But the editor itself is always referencing top down at support, bottom up at midspan, and then at the anchor it's top down from the at each end of the tendon. Okay, so we'll say this is 7. We're going to say this one is 7. We have 7 there. Same thing on this side. And then I'll switch this to 6.5. And just Windows select these ones. And those. And then we also want to, since there's a break in the slab here, these will also be, referenced similarly to, because this is discontinuous, this is continuous, again discontinuous here, so these will be 6.5, and then this one is okay, that's 1.5 on both sides, 1.5 there, and then 3 and 4 spot there. Okay, going back to our view, just to kind of see what this is looking like. Notice again, I'm I'm referencing now from the display manager showing the control points. If I go out of tendon editor, notice that this says 6.5, 1.5, 6.5. If I close that and I have the display manager on, which is currently showing control points, this actually changes from bottom up to 29.5. So that automatically will update the CG based on the view you're looking at the tendons in. On the perimeter of the slab, we're going to use 10 strands. So I'll just take this tendon here and I'll copy it. I'll Control C, Control V again, just copy one there and one over here. And we're going to modify that cable. So I'll just do this using the tendon properties for that one specific cable. I'm actually going to move it in also because right now it's on the edge of the slab. I'll change this to 10. The CG in this case is probably something different than 7. I'm just going to leave it at 7 for now. We can modify it here in a moment. And I'm also going to move that off of the slab edge. So to me, the easiest way to do this really is to just Control C, Control V and use snap to nearest and just model another cable once it's been modified and delete that one. So the same thing on this side. If I actually just delete this and I'll come back over to this cable and just copy that again. It's identical to this, to the left side, so we can copy that over again. And then finally, if we go back to our design cut, this is a spandrel on this end, so the CG centroid to top fiber is 7.75. So we'll change that. I'll go back into the tendon editor. CG, we'll say 7.75. We'll change both ends for 2 cables, 2 of the end cables. Okay, so this is just our starting point. This technically should satisfy the precompression. We don't know yet what balance loading level we're at, nor do we know where we're at with allowable stresses. We could use the optimizer to fine-tune the tendons once we check the stresses. And so now what we want to do is actually make and create our tendons for the one-way slab direction. So I'm going to turn off my strips, and in the one-way slab direction, since I created strips of 10 feet, I'm actually going to add tendons for each strip. I think this is the most direct way to just get distributed cables inside of our uniform strips in the X direction. So there's another reason for this when we're checking pre-compression for the simplified method, or the number of tendon method as we call it. The simplified method takes the total number of tendons times the force divided by the area. So sometimes what happens is, due to the spacing, if I was to space tendons every 4 feet, for example, you might get a imbalance in the number of tendons per 10-foot strip. One strip has a high pre-compression, the other one might look low, and it's just due to the way the program is checking that particular check. We have another option for pre-compression, which is used as the FEM results. We take the total axial force in plane and divide it by the area of the section. So there's 2 ways to do that. This, what I'm going to show, is probably the most direct way to handle the tendons. So if we take 10 feet times 12, so 120, and we multiply 120 times the slab thickness. I think this is a 7-inch slab. Yeah, it's 7. And let's assume we want a pre-compression of 125. That's 105 kips. So 105 divided by 26.7. We need 4 tendons per 10 feet in this case. I'm going to model the first tendon at 5 feet. So I want this tendon to basically be centered in each of the strips. If we turn the strips on in this direction in the X, I want to center these cables, let's say, I don't know if we should center them right on the support line, but we'll pull it off of the support slightly, this support line here. So we'll go ahead and model another cable. I'll start that there, and I'm going to use snap perpendicular in this case, and we'll just snap perpendicular to each of these banded lines. So here we're just representing, each line I'm drawing here will represent four cables per strip. Okay, and for this set of cables, I'm going to modify the CGs to the number of cables is 4. They're half-inch diameter strands. Stressing is 26.7 kips for our effective force. And then I'll change the CG to 1. So I'll use this typical row here. I'll change that to 1, change this to 1, reassign the end to 3.5, and then on this side we'll say this is 3.5. So this is the base profile we'll use for the distributed cable. Now you could do, if I wanted to model 2 tendons times 2 in each strip, I could model, for example, a cable, I could model 1 tendon, 2. So this is 2 and 2, and then another 2 and 2, and so on. Here I'm, again, just representing 4 cables by 1 line in the model. I'm going to take this cable, I'm going to I'm going to copy this in plane using a reference point. So I'll use the support line point as a reference, and I'm just going to go in and copy this, and I'll copy it 17 times. Okay, and that just copied each of those tendons 17 times. The only modification we'll make is actually changing this cable. I'll use 3 out here on the ends, and we need to copy that one up to the strip also. So I'll just copy that tendon, let's say right there, and we'll change that to 3. Okay, so we have all of the tendons in the model. If I want a kind of a clean view of this, I can go back to my default display, turn the tendons back on. In plan, we could check CGs, we could make modifications here. One thing I would recommend you do whenever you model PT in any builder model is, after you've modeled them, go to the visibility tab under the render model, and in this tab I like to turn off the walls and columns and go to just a wireframe, and then I might scale this in the Z direction, let's say by a factor of 3, and this just helps see the overall profiles for our cables. And this helps you kind of detect and catch some areas where you might have invalid drapes or different shapes for a profile. But this is where we'll start. So I'll close that. I'm going to just go ahead and open up our cheat sheet here. So we've done tendon modeling. We're now we've added loads. Our model is essentially built. Now we want to mesh and analyze the structure and design the sections. So remember, this is for gravity design. So we're really going to focus on first satisfying the PT result, which means we're going to check serviceability level conditions for the slab and the beams. We might check just some initial deflection, not initial as in the initial stress condition when we transfer the force, but just what is our deflection under linear elastic conditions for total service. And we might make a prediction of long-term deflection just by applying a multiplier on top of that and see where we're at. So we'll also check precompression, balance loading, allowable stresses, and kind of give you a flavor of what that check is like. And then we'll go back into generating reinforcement to meet minimum requirements for beams and one-way slabs, and also strength requirements for the members. Okay, so I'm going to go back to my default display. I'll turn my tendons off, get rid of those dimensions for a moment, and we want to mesh the structure. So if we go to mesh, we have several different options here, and a user who might be new to the software might wonder, well, which options should I use? Whenever you have a single level model like this, where you're really only worried about, let's say, the horizontal elements and the design of those elements for this particular instance, I would not use advanced meshing. Advanced meshing is really only useful when you have a multi-story model with openings and you want to mesh around the openings, so you get the behavior of the lateral, let's say the lateral behavior of the structure, considering all of these punctures in walls. So in this case, we have no openings in our walls. We haven't defined them. We really only care about what's happening, in the slab and beams themselves. So we're going to just use simplified. Once we use simplified, we have a decision to make on whether we want to use a sparse mesh, which is more of an organic mesh, which the program tries to economize or make the mesh the most efficient that it can in reducing the node count for the entire mesh. Or you can go to uniform, which uses a different set of constraints and parameters to generate a mesh, one of which is just maintaining this particular size here, but maintaining an aspect ratio of the quadrilateral elements for the mesh. So this will give you probably the least amount of nodes. It's typical to use this unless for some reason you're trying to get perfect symmetry in a result. You might want to go to a smaller uniform mesh. For example, if you have balance loading that is 60% in one bay of these beams, and in the other bay it's 61%, and you're worried that you want each one to be 60.5%, well, to get that level of refinement, you probably would have to go to a uniform mesh and mesh this at 1 foot. So we'll just use the defaults here. I'll save and mesh the slab. Okay, this mesh looks fine. I mean, it's actually quite symmetric itself. You can just see that the shells have more, it's more relaxed in terms of their size and their aspect ratio and so on. So this is the mesh we'll use for this model. If we go to the load combinations, we're only going to analyze this for this particular run. We'll analyze for service total and service sustained and also initial. I'm going to avoid strength for now because we want to fine-tune any post-tensioning that's not meeting the requirements, pre-compression, balance loading, for example, or just meeting the allowable stresses for the members. So we'll run this for these 3 combos. I'll go to analysis, execute the analysis after we've meshed, and here I can select the combos I want to run the design for. And we'll select OK to run the analysis. Okay, so once the analysis has been run, at this point we could actually obtain just general finite element results for the model. If I wanted to look at deflections for the combinations that I ran, I could go into the result browser. I could select, for example, service total. Under analysis, slab deformation, what's the Z direction deformation for the slab. And we can see these deflections. Clearly, it looks a little bit odd only because there's a clean break here, right there and right there. And obviously that's happening because we have an opening there, and we have just completely different deflection in this outer bay versus the inner bay because it's twice as, the inner bay is twice as long. But if we look at these deflections under service total, maximum deflection out here between beams is around 1/4 of an inch. And if we look at the deflection right on the beam, it's obviously less. I could go into the beam actions. Let me turn off the contours, and I'll go to beam deformation, Z deflection, and I'll rotate this, or I can just make this graph so that it's in the XY plane, and you can see the deflection of the beam itself is only about 1/10 of an inch maximum here in this these longer spans. In the outer spans, it's actually 0.14 inches there in the outer spans. I imagine that's because of its single span versus this is a continuous member, 2-span condition interior. So these are the beam only deflections. These are not the composite T deflection for the member. But if you were to overlay the contour on top of this, you have to maintain some level of compatibility in the displacement at the exact point we're looking at. And if you look at the slab contours at that same point where you have maximum beam deflection, the slab deflection would be the same. So there's different types of results you can access, in this realm after we've analyzed that are purely based on just either shell elements or frame elements, and we've presented an example here with a contour for displacement and then a line diagram, for example, for the beam elements. We're going to take it a step further in order to evaluate this on the basis of design strips, where we have these composite members, a flange with a beam or a T-section, and we have to, in order to do this, we have to process the design of the design strips. So we'll go to floor design. We'll design. We've already generated the section cuts and the tributaries. Those are generated here. If you want to see those more clearly, you can always go into this tributary option. This kind of shows me the colored tributaries of each of the directions X and Y. Also, you could go to reports, design strips, and this will show me even more clearly what these design strips are. They're hatched in this view, so it's a little cleaner of a view to show it this way. So these are the strips we're going to design. We'll go back to floor design and design the section cuts. Now the deflection that we just looked at, that does not consider the long-term or cracking effects in the members. We haven't set the model up yet for that, but we could make a prediction. The max deflection was around 0.25 inches. If we apply some multiplier to that, I'll just say the multiplier, the creep might be a factor of 2, not considering any compression reinforcement. So if we take instantaneous plus creep of 2, we get a factor 3 times the max deflection, which is around 0.75. In this case, that likely would obviously work over a span of 60 feet for total deflection. There are ways to predict that more closely in terms of generating crack deflection and long-term deflection combinations in the combination input. So once we've designed the sections, now we have results for not just beams or slabs individually, but for the design section itself. If I come back over here into the result browser, and I'll go ahead and collapse that and then expand out the design section. Let me turn on this Y direction. We have several different options here. The first option is deformation. So whatever the selection is for my load combination, I can show the deformation relative to the span. To give you an example, let me go, let's go here. This span from here to here is 30 feet, but in reality the span is defined in this type of a result. The span is defined as the input of support line vertices. So I clicked here and I clicked there. That defines this span. So we take this span, which happens to be the 30 feet, and we take the 30 feet and we divide it by the maximum deflection at any point along that design strip. Here it's 0.14 inches, and that gives us the 2658 value shown here. If I had modeled this this strip from, let me just zoom out a bit. If I had modeled this strip, for example, from here over to here, then these values would be basically, they would mean really nothing in this case, because the span would then be, 120 plus 60 would be 180 feet in terms of generating this result. So make sure when you generate the spans, you're generating them as they really are in terms of the location of the supports. Otherwise, this result becomes meaningless in a way. Okay, so that's the first thing. The program color codes the check. Here you can see all the sections are green. Let me change this over to the X direction. The same thing will happen in this direction. And this is checking against, if we go to display and we look at this value, maximum span deflection is L over 360. So clearly these all meet that requirement for this particular combination. If I change the combination to, for example, sustained, then we update this result, and it again will check against whatever this setting is set at currently. So that's one way to check the deflections on a span-by-span basis for design strips. In addition to deflection checks for design strips, we can look at any action for the selected combination. Let me change this back to service total. If I wanted to check bending moments, here it's somewhat difficult to see because the diagrams are quite small, but this is really just showing us max min value on each strip. I have max min selected as a default. If I switch this to numerical display, it will show me the moment for every design cut on each of the strips. Okay, and I can toggle this again over to the beam direction, which will show me these values also. Okay, ultimately we want to check for the PT design of these members. We want to check, first we'll check precompression. We want to make sure we meet the precompression required for the design. There's a question, are the moments, displacements, and I'm just going to read that, Marcos. The moments, displacements, etc. of the design section is the composite action. Yes, it is the composite action. So if I'll give you an example, if I go back to the design section bending moment, the composite bending moment for this section right here would be 710 kip feet. This is for service total. If I turn on the beam bending moment, I'll go to beam actions. This is moment. It's about S. It's hard to read that because there's an I and J, for every frame element on there. So this becomes a little trickier to read. But you can see right here that's negative 314. That's the maximum. If I turn off numerical, the maximum moment there on this beam is 314.85 kip feet. The notation's different because of the way we generate the notation for the frame element versus the composite design cut. But about half of the moment, let's say slightly under half of the moment, is actually from the beam, and then the greater portion of the moment is from the integrated slab element. Okay, I'll turn off the beam. Coming back to stresses, you can see right now the precompression setting under display is set to 125 for minimum precompression. And if we go back to analysis for service total, these both say it's no good. And say, okay, well, what's going on here? I'll check number of tendons first. And you can see there's two areas where we get this weird kind of sudden drop in the precompression for the design cuts. If I look at the other direction, again, we get, you know, something here that doesn't quite work. And if we the selection I made, number of tendons, means that it's taking the total area of a design cut and it's dividing the force, the summation of the force from any tendons in the design cut divided by that area. That's how this is working. So so here we set our minimum precompression initially to about 130, 125, 130, I think. And this drops down to about 95. Well, clearly the reason it's dropping is because we didn't consider the fact that there's a beam on this interior frame line. We had 4 tendons. These tendons here, this is number 4 tendons. And the design area for this interior frame, the area is actually 1,115. And for a frame without the beam, it is 840. So if we take 1,115 over 840, we would probably need to bump those number of tendons up by about 40%. I would want to add 2 additional tendons for this interior frame line. So this is easily solvable. I would add the tendons or just increase the number of strands for that and then rerun the analysis. And just for sake of time, I'm not going to rerun it quite yet. I will modify it to 6. Now this could happen automatically using the optimizer, which I'll show hopefully here in just a moment. I'm going to go back to this other direction where we have this sudden drop. We have tendons there. There's clearly a tendon that stops right there and it gets, you know, it's extended here, but we say, well, why isn't that tendon being considered, right? There's no precompression in this cut there, and I think that's the only cut where we have that loss. To investigate why this is happening, we have to show something slightly different. So I'm going to turn off these results for a moment. I'll turn the tendons off. Actually, I'll keep the tendons on, and I'm going to turn on the frame elements. And you can see that this frame element right there, that frame element starts right here. This is the first frame element or the last. It's probably the last because this was the end of the beam in this beam. And notice that I modeled the tendon incorrectly. I'll call that out. I modeled the tendon to the edge of the opening. It doesn't actually extend out to the center where that frame element ends. So what the program is doing is when we discretize the tendon to the frame elements, we basically break this tendon into a bunch of segments and consider it as an internal resisting element internally for the solution. This tendon is actually being truncated. It's getting cut off here. We're pushing it to this location right there. This can be shown if we go to the result viewer. And in the result viewer, if I go into a kind of this transparent mode, and I'll go ahead and turn the tendons on, this shows me the actual location, analytical location of the tendons, and you can see that is happening. This tendon's getting pushed. It's really modeled out here, but it's being moved to that face because it doesn't actually extend out to the edge of the beam. Okay, so I realize you know that that took us down a rabbit hole, and that might be hard to troubleshoot. So it's really important to either understand what's happening with the discretization of the tendons, or to make sure the modeling is sufficient. And in my case, I didn't model these properly. So what I'll do is I'll just move this to there. I thought I had modeled it there, but maybe not. Let me go ahead and turn off the. This one's modeled to, yeah, that one's okay. Let me just go down this string here. That one there looks okay. This one's not. I'll model both tendons to that center point. Okay, and this is happening on both sides. So I would also need to change it over on this side. I'll go ahead and turn off the elements, the frame elements, and my tendons. And we'll go back into some results. So we know how to kind of take care of the precompression issue. If I look back at the beam precompression, I mean, everything is right at about 150 or so where we targeted it as. So everything here is really okay other than this strange anomaly relative to the other sections where we know exactly what's going on there. But the next thing we may want to check are stresses. I want to know what my stresses are, top and bottom fiber stress for surface total. That's probably the controlling condition here. So we'll go to the top stress first. And we can see just by meeting, right now I would consider us meeting minimum precompression. And when I check the top stress, you can see in this interior bay, the beams are actually fully precompressed at the top. I would expect that at midspan, but over support, I would actually expect a little bit of tension. So this tells us that the beams might be actually slightly oversized, because typically we have a little bit of tension on the top fiber over support. Out in the outer bays, we do have tension here. This is top fiber, so we have some tension on the top fiber in the outer bay. That probably means we're overbalancing that particular bay. This is a short bay. If I go directly to balance loading in those bays, you can see this clearly shows us overbalancing the bay because we maxed out the drape to begin with. So we'll have to fine tune that and make that work. Bottom stress, again, we have high compression on the bottom fiber, which again is an indication that we're actually overbalancing the span, and that's happening on these outer spans. On the inner spans, I think we're okay. At bottom fiber, we actually have very little tension, if any. We have a little bit kind of shifted towards the top side of center. So these two interior spans look okay on these beams. If we check the balance loading on those interior spans, for the most part, 90, 80, they're hovering right around 80 to 90%, except for these outer spans. And then we have a couple of locations here where it's a little high on the interior. So our biggest issue with this model really is overbalancing the tendons out here on these outer spans. We know that precompression can be solved. That's just more of a modeling issue. The stresses are okay other than the fact we're overstressing the outer bands. And then balance loading, we have some problem areas here to fix. In the other direction, in the one-way slab direction, we have a little overbalancing out on the corner conditions, but everything else is less than 100. Our target here, the balance loading maximum, is 100%. We're only graphically checking against the maximum, not the minimum. So if you select any of these different options, you can always read the description down here, and it will give you an indication of what's happening. The reason we have balance loading minimum and maximum, precompression min and max, for balance loading we only check against maximum. The graphical check is done against maximum. For precompression we check against minimum. So in the current version we also need to have maximum balance loading and maximum precompression in order to preload the data in the Tendon Optimizer. That's why they were actually added to this dialog. And the Tendon Optimizer can be used to satisfy some of these conditions. I'll show you that lastly. Okay, so let's, by the way, in the one-way slab direction, top and bottom stresses are also satisfied. So we have a little bit of tension in the spans in the one-way slab direction, and then top stress is still meeting allowable. So if we were to use the Tendon Optimizer, our kind of the biggest concern here is the overbalancing, let's say, in these outer bays for our beams. And I'll switch back over to there. So we'll take one example. We'll take this example, this 332% overbalancing. And what we want to do is we're going to use the Tendon Optimizer to try and determine, how we can, what the CG would be required to be, to reduce that down to an acceptable level. So I'll go into Tendon. I'm going to go over to Optimizer. And in the Optimizer, I'm going to generate my settings. I'm not going to go through these in detail. I'm just going to quickly enter some settings here for sake of time, but the program is going to create 3 virtual design cuts. One, the design cuts are not that thick, so we'll do 1, 2, and 3. This would be like A, B, and C. And it's optimizing for these 3 locations. The 2 end locations near support are based on this percentage of the span length away from the face of column. So I tend to use something smaller than 5% just so I'm more in line with where there is a design cut on the actual strip. So the optimizer, what we're doing is we're kind of just isolating one span and we're pulling that out of the finite element model in essence and optimizing it based on this input, and then we can plug the result back into the FEM model. So we'll say this is 2 feet, or excuse me, 2%. We're going to optimize for load balancing based on self-weight plus dead load. Okay, the pre-compression range we'll say is between 150 and 300. I'll say 400 for the beam. And load balancing we'll say is 50 to 100 for these exterior bays. The combination is service total. The criteria is really a beam. And then we can decide how we want to output the stress, either ratio, factored, or actual. So once that is set up, then I'm going to go and let me turn the tendons on. I want to optimize this beam tendon right there. So we'll go ahead and we'll go to Optimizer, and it says changes have been made to the settings. Do we want to save? Yes. I'll select that tendon to optimize. Let me reset that. So I'll select this tendon. What's the tributary width? I think it's 30 feet. Okay, and you can see the virtual span that the program is generating. It's this blue box. There's tendon or cut A, B, and C. This will show us what the tendons are currently in that beam. So we have 18 strands, 26.7 for the effective force, and the CG is 1.5. Now this over here gives us an indication kind of where we're currently at. This is the current force. It's 481 kips. The maximum load balancing range would actually at a static CG, the load balancing maximum would only require a force of 149 kips. So there's a gap here between the required load balancing and the required precompression force range, which is problematic. That means we have to lift the tendon up in order to adjust this. So this gives an indication of where we're currently at. We have 480. The estimated really is 480. It already meets stress and pre-compression. Our main issue is load balancing. But what I can do is I can edit this and I can change the CG. So if I change the CG, let's say to 3, and I estimate, we're now at 306, but our pre-compression and stress are still okay. And I'll lift that thing way up to, let's say, 12. And now we're down to 202. We're still okay with pre-compression and stress. Let's go all the way up to CG of the beam, which is 18. 132. Again, the stresses are still okay. I'll go up to 22. And now we pass. The percentage is 86.68. We started at 323. Okay, so I'm using this as a very quick tool to estimate what a change in CG would do to both pre-compression and to stress. If I go back to the original, I think it was 1.5, this fails, right? So let's just say we're going to use 2022 here, and I can exit out of here. I'm just really using that as a tool to determine where I need to be. And now I would need to go back and change the CGs of these two, or these cables here. So I could go back into the editor. I'm going to say this is a CG of 22. I think the beams are just too deep in this in these outer spans, and I will basically window select that. It's hard to see that change. I have too much happening here on this. So there's 22. Oops. Same thing there, and then over on this side, change those, and I'll close. Okay, once we've made the changes to our tendons, we would want to reanalyze. So I'm going to go ahead and execute one more time here. Here I'm going to execute for everything. I'm going to assume that the result of this is going to be satisfactory, and then we'll finish up with showing the output for the reinforcement and the strength design. Once the tendons are where we want them in terms of their profile and the number of strands, then we would go in and check strength, because that affects the capacity that's generated in the member from the post-tensioning. And once we know the capacity being produced by the PT, we can determine how much additional reinforcement is needed to meet the envelope of the factored level moments and forces in the member. Okay, and then we'll go back to floor design, design the sections. So running through this process, you might have a few iterations you need to go through to fine tune a model like this. There's another question. Would it be applicable to limit the strip width with the effective flange and then use middle strips in between? Yeah, that's something, Marcos, that we had covered somewhat last week. To limit the effective flange, we would have to use splitters, and we might, add splitters here. But in so doing, we leave this area kind of in the middle without any design. So we would have to put in another support line here and then that support line would in essence be designed similarly like to a middle strip for a two-way slab. So that is something that you can do. I mean, again, I mentioned last week that the effective flange is just more of a way to create a uniform stress distribution over the beam flange. In essence, it's mainly used for an isolated beam design versus FEM. In the FEM model, we're already integrating over a non-uniform moment distribution for the flange. So, but yeah, you can use that option if needed. Okay, so, let's reset here and we'll go to the beam direction again. If we check the pre-compression, notice this side is now okay. I didn't go back and change that side. In the other direction, we had updated the number of tendons from 4 to 6. Now we have some weird something weird happening here where the pre-compression appears to be less than allowable. I might have changed the setting here. Yeah, I changed that to 125, or excuse me, to 150 versus 125. Originally it was at 125, so this would update. These should all be okay versus 125. And then we had a couple of regions where the balance loading was not good. If we go to balance loading simplified, I'm going to use the simplified option. Again, I'll go to the beam. You can see these are now reduced down to an acceptable limit. These are still a little high, so I may have to reduce that even more. And then these are also quite high. Ultimately, after you've gone through the iterations, satisfying stresses, balance loading, pre-compression, you need to design the reinforcement for the members. So the program has already designed the reinforcement for the members. If we actually go into calculated rebar plan, we can generate a rebar envelope for strength or for service or for everything or individual combos. So I'll just do the envelope of everything. This would be the maximum required rebar based on minimum requirements and rebar necessary to meet the strength of the member, meaning to meet maximum moment or any axial tension in a member. And you can see this generates a lot of rebar, right? So we have rebar both for the beams and for the one-way slabs. And the best way to isolate this would be to go into the reinforcement or the rebar tab or ribbon display manager. And I'm going to isolate to look at just the Y direction. That's the beam rebar. So this shows me beam rebar. Whenever a design strip is set to beam design, the program always groups the reinforcement. So it doesn't show it as distributed over a flange, it just groups it. And so here you have 3 number 8 bars basically for all of these beams. In the bottom, red is bottom reinforcement, green is top, and you have 11 number 5s for the beam on top at supports. Now this obviously could be distributed over a range at the top because it's inside of the flange. So we could modify these to grouped. I could go, or excuse me, from grouped to distributed. I could take this bar, change it to distributed, and then say, okay, this is 15-foot extension on either side, and this becomes a grouped output. So there's ways to modify and manipulate the output of rebar. The reason it's shown as grouped, again, is because this is set to a beam design criteria. If we look at the other direction, which are all one-way slabs, we have something that looks like this. Everything is actually distributed except for the top rebar. The bottom rebar is distributed, top rebar is still grouped in this case. You also have this green again is top, red is bottom, and then you have blue. And you say, well, what is the blue rebar? The blue rebar, the color trigger actually comes from whenever a bar extends into two different thicknesses, if the start point and the end point of the bar are located in two different elements with different thickness, then this will trigger blue. It's really just a warning to the user for detailing. So here you can see all of these bars on the perimeter actually go out, and they get extended outside of the slab because of some bar extension rules that we're using. In this case, in reality, these bars would likely just be hooked out on the perimeter. They wouldn't extend out here. Well, actually, the slab edge would be out here, so they might actually extend like this. But analytically, the slab edge is here, therefore it tags these as blue. Okay, so it's not a analytical problem. It's really just a detail warning for the user to pay attention to those bars that are colored blue. It also happens over here. You can see like this is 3 number 8s by 24, 24.5 feet, and these are at the bottom. Remember, this strip right here actually is on a beam. So if I take a cut through there, you're going to have a stem like so. And this is saying that these bars are distributed over some range, which is really just the tributary. It's this distance here. So this turns blue because the bar distribution goes from slab through a beam back into slab. In reality, these 3 number 8s, you can't distribute one here, one in the beam, and one here. These 3 number 8s actually belong inside of this beam stem here. So that's just another, it's kind of a hard code setting that we use when we generate design strips for beams versus one-way slabs versus two-way slabs. In reality, what we should have done initially is we should have set this strip in this direction. This one should really be set to a beam. It's set currently to a two-way or a one-way slab. It should be set to beam. Okay, if you want to change, I mean, this is a lot of rebar, and you could probably go through and just figure out some pattern here. I need, number 4s or number 5s at 12 inches on center. You could go back and input rebar as base reinforcement using some of these tools for modeling base rebar, and then the program would just add rebar as necessary if the base reinforcement doesn't meet the requirements. So there are ways to do that. Okay, so that's the reinforcement output, and we're going to go ahead and conclude today. I think we've run out of time today, but we'll conclude there. I'll just go ahead and I appreciate everyone for joining us today. I'll answer questions now for the next 10 minutes or so. There is a question that says, what about shear reinforcement for the beams? So for the beam shear reinforcement, it's not out in front as is the longitudinal reinforcement. There's basically 3 ways to produce shear reinforcement in the program. And as an aside, we're working on improving the way that we handle beams and the reinforcement of beams and the design of beams in the program. That's coming. But for now, for shear reinforcement, 3 ways to do that. The first way, which I think is probably the best way, if we turn back on the strips for our beams, I'll take this one for example, and if I go into this elevation view right here, there's a little tag here and an insertion point. Let me go back and generate the rebar. Okay, try this again, Marcos. I'm just trying to turn on the view of the, well, I'll just double click there. All right, so here's the strip. I'll go to this option to generate an elevation for that strip, and if I click there, this will actually show me an elevation of the selected strip. So you could produce these elevations and then export them as CAD files. But this shows me shear reinforcement. We have 2 at 17, and it's extended from the face of this column 1.38 feet. There's 12 at 23, extended 21.54 feet from these anchors, which are usually the faces of the columns or walls. That's one way to generate shear reinforcement. Another way to generate the reinforcement would be through builder sum. So for any design strip, you could go into the builder sum tab. That can also be done for all design strips at once. There's an option on one of the ribbons for this, but here you could produce a summary of shear reinforcement here. This is a summary, so it's not detailed. It's hard to see exactly where the reinforcement goes, but that gives you something similar to adapt PTRC. If you open builder sum without clicking on a single support line, then this lists all of the design or the support lines, and you could produce, a graph for each one. The last thing to do would be to generate a rebar report. So if we go into reports, design strips under design section rebar, for example, for strength, dead and live, you can choose how you want to generate the report. Here I'm going to generate the I'm going to say don't generate an envelope. Here this envelopes the selected reports. This in essence creates a Word report that defines every design cut for every single section in the model. If you select only a handful of support lines or one support line, it would only generate the report for that support line. And in that report, you have the area of shear reinforcement and the spacing. So that's more of a tabular output. The next question, does PTI or ADAPT have any recommendation on how high the tendon CG can be placed in order to satisfy balanced loading requirements? Are there any issues with lifting it above the CG of the section? No, Kirby, I mean, it would reasonably, we had to lift these particular tendons up so high because the beam was so deep. I didn't change the depth of the beam on the outer spans. So we ended up going above the CG. The effect of the post-tensioning is based on the profile, the relative profile of the tendon. So if we have a beam, let's say here, and the CG of this beam is like so. In our case, we actually had a tendon that was something like this. This tendon, if this is a simple parabola, would still provide uniform uplift, let's say, on this beam. Okay, so in terms of the imposed uplift and the effect of the PT on the beam, it's based on the relative drape from point 1 to point 2 and point 2 to point 3, and that changes if you have inflection points. This does change the behavior of the beam from a strength standpoint. Obviously, if this is a flanged beam and you have a big lump of PT up here, then and maybe the compression zone is right there. I mean, that changes the mechanics of the section, and you might not have a very efficient section in terms of the strength design. But to answer your question directly, as long as the endpoints are not lower than this midpoint, I think it's acceptable, and you also have to maintain proper covers and so on, for the PT. But yeah, this is a little bit abnormal only because these beams are just simply too deep for this particular member. It's just an oversized beam. All right, let me check our question list here. The question is the flange the flange given by the design section is bigger than the effective flange. So the CG of the beam may not be the value given in the design section. So we take it as in the design section. That's, again, the notion of effective flange in ADAPT's opinion does not correlate with finite element modeling. So you have a decision to make. Either you use the full flange, which in this case we would anchor the CG or we would anchor the tendon at the CG of the full flange, or you introduce design or splitters, let's say, and model your effective flange, and then you would have to then, you know, adjust the CG relative to the effective width of the beam. And that would also bear itself out once I add splitters to this beam, for example, and I regenerate the strips. I can calculate the effective, you know, width, or excuse me, I can calculate the CG of this width, which is now the effective width, and you can adjust the anchorage of the tendon relative to this strip. You're going to have another strip here, and then you're going to have a middle strip in here. Okay, we have a difference of opinion on that. I mean, if you look at our program Adapt PTRC, when we, by default, when we anchor the tendon, when we actually go through the design and the program designs the cables, even when you have, let's say this is the full flange, and you model in Adapt PT the full flange, and then you choose to allow the program to calculate the effective flange, which might be here, our program Adapt PT by default will actually anchor the CG based on the effective flange, which is here. And there we do this because this force in the cable that's here, let's assume there's a cable, I'll draw this in pink, there's a cable here and there. This force doesn't just magically stop at the effective flange location, it extends into this zone. That's why we base it on the full tributary, this CG, because we're depositing the force in over a full tributary, which gets split up like so. If the user wants to base everything on effective flange, we have options in that program, Adapt PT, and even in Builder here, like I just showed, where you can base everything on this value shown here. So it comes down to, you know, to what the user feels more comfortable with. We're not going to tell a user you must use full tributary, even though the code allows you to use full tributary for post-tension members. For post-tension beams, it completely waives the requirement for effective flange. There's other research-related factors involved in that as well, but it's a lot of that's shown in the commentary of the ACI code. Other questions? You can design up to, I would say, class T. When you get into class C, I mean, if I wanted to design this beam as class T, which is, you know, anywhere between, let's say, 7.5 and 12 squared F prime C, ultimately it's kind of a manual input. I would just go back into the allowable stresses, and I would adjust my allowable stress here. And you also are required to then check cracking in the beams if you do this. So class C, which is cracked above 12, requires additional kind of hoops you have to jump through. You have to base the analysis on a cracked section property, which you could do in the program. You could assign multipliers to elements to kind of simulate the cracking, where you're reducing the stiffness of the element. You also have to provide, you know, crack deflection checks and some prescriptive reinforcement in the side walls of members for a class T design. So yeah, you could do that in the program, but just be aware you have to change kind of the target you're working with when you do that. Okay, there's a question. Can I copy and paste components from one model to another? And this Yes, Marcus, I will show you how now. Let's say that I have a model, and let's just say I want to just copy. I'll first start by copying the slab, or by creating a new model based on an IMP file. So let me set this up. We're going to take this model, and we're going to export an IMP, and we'll call this just model 2. I'm going to go in and create a new file, so I'll open up a new instance of the program. Okay, we'll go to File. Here's model 2, and I'll just create level 3. Okay, I don't want to bring in any load cases in this example or combos. I guess I could, we're not really using them. So we create level 3 in this model. Notice that the program brings in the rebar, the slab, the beams, the openings, the loading, everything is in the model except for, let me go to my default display. The only thing that didn't get brought in was the tendons are there, by the way, and that's by virtue of having this. Well, if I'll say this, if you want to export this out to Revit with tendons, you actually have to turn on export tendon segments in IMP. So if we're going builder to builder, the tendons will be brought in. If we're going from builder to Revit, we have to set this option here up in order to export the tendons. So everything is here except for support lines and splitters. There are no support lines and splitters in this model. If we go to floor design and try to turn this on, nothing is there. So what I'm going to do is just save this file. This is the new file I created. I'll save as. We'll call this model 2. Okay, I'll close it. So I just did that to establish another model, right? And we're going to copy from this model to the other model. So I'll turn on my support lines and splitters. I'm going to go home, select by type. Let's do, we don't have splitters, we'll just do support lines. And I'll just press Control C, or I can go to modify and copy. There are ways to copy here, so we'll copy. I'm going to go now and open the new file. They cannot be opened in tandem, and I'm just going to press Control V, and I'll press O for origin, and there's the copy. Okay, so that's how you can copy and paste. I mean, I could copy different types of components from one model to another that way. Miriam, your question, in Class C, should we change stiffness modifiers, or the crack deflection takes this into consideration? The crack deflection check only applies to horizontal elements like beams and slabs, and it's a post process. So you could run the model first, given your current condition, run crack deflection, determine the level of cracking, and then go back, and you could then apply modifiers to the beams and the slab for that level of cracking. That becomes somewhat tedious and difficult, because if let's say that you're really just getting cracking around these supports, and maybe you lose stiffness in midspan, there's a contour that you can look at to actually show where it's cracking. If these areas that I've circled, or let's say they're cracking to a level of 50%, when I go back and I want to run this for Class C, I have to apply a stiffness modifier now to the slab, but I only have one slab modeled. So I have to be overly conservative and say, oh, this whole slab I'm going to use 0.5 as my modifier, where in reality we only have to really modify these zones. So that becomes a little tedious, but you can do this if you, in order to do localized modification. Then I would actually have to model different slab regions. I would say, okay, I'm going to model slabs over each one of these columns, and I'll modify their stiffness by 50%. I might model another slab here, another slab there, and then I would fill in another slab kind of all the way around. This slab that's filled in, we retain the 1 modifier, and then everything else we would assign as 0.5. So it becomes tedious. You would also have to modify, walls and columns based on some assumption of cracking for those elements also. One nice thing I'll say is we do plan on taking the crack deflection result, saving it as a usage case, and then having the ability to then reapply the loss of stiffness, basically I effective to a new run. And that would completely eliminate what I just outlined for you, where after you run crack deflection, we just automatically store those values, and then the user could then reapply as a modifier to every component that we check for the slabs and the beams. All right, we'll go ahead and conclude. Thanks, everyone. I appreciate everyone's time today, and we'll get the video up as soon as possible. We had a few technical difficulties with last week's video, so we're still trying to sort those out, but we will get those up as soon as we can. And if you have questions in the meantime, feel free to contact us at support@adaptsoft.com. Thank you.